Okay, we are continuing with our theory questions. This is a calculation question, okay? So we are kind of skipping it. I mean, the drawing of the FBD is not the calculation, but we know that in here this is calculation, okay? This is like the superposition, but it's we don't have values. I mean, you won't get values. You've seen this question being done a lot of times. So it's like the first version, and then you can actually get where you have P1, P2, P3 being given as being given with their values. That it becomes even nicer that way. Anyway, let's come to Gauss law here, which says here, state Gauss law, give its mathematical expression, stating each term. So this is another easy question for us. It's saying we should just state what Gauss law says, and then we should give it its mathematical expression and state what each term is. Now, Gauss law just says that the electric flux, okay, you can just say the electric flux through any closed surface, the electric flux through any closed surface. It's about flux. Flux is the field lines that are going through something. So here, the electric flux, the electric field lines that go through any closed surface, the number of electric field lines, like how many electric field lines or how much you have. So the electric field lines that go through any closed surface is equal to the net charge Q enclosed, which is enclosed just means inside, enclosed in the surface, divided by the permittivity of free space, which is mu zero. Okay, this is going to be the Gaussian law, the Gauss law. It says the electric flux that goes through any closed surface is equal to the net charge enclosed in the surface, or the total charge inside, divided by the permittivity of free space. How is this? So now when we put it as a formula, we just put flux is going to be like this. It is like this, the flux, okay? And this is the Gaussian law. It will be just saying the flux, it will be equal to Q, sometimes you see them say Q surface, but this just means the net charge inside the surface, enclosed in the surface, divided by mu zero, okay? So you can say here that flux, this is going to be, here when we put it like this, we can just say this is going to be the electric flux, okay? This is the electric flux through any closed surface. Okay, then you are going to have Q, which is the net charge enclosed in the surface, so the charge inside, okay, divided by mu zero, which is the permittivity of free space. Okay, now we can go, here it says find the capacitance. We are not going to do calculation, maximum charge, blah blah blah. Here is number 8. Let's do these defined questions. We love them. All right, defined questions, are they good for us? Yes, they are. What is the first thing we are defining? Electrostatic work. We've got like 4 things that we define in week 3 and 4. Okay, one is work. Electrostatic work. What is electrostatic work? It is, you're going to say it is the we can say they say define electrostatic work. Can say it is the work done. Can just say it is the work done by an electrostatic force. By an electrostatic force F, by an electrostatic force F, okay, in moving a given amount of charge. What we move is charge, okay? In moving a given amount of charge from one position to another, okay? From one position to another. This is going to be the what? The electrostatic work. Work done by an electrostatic force in moving a charged particle or a given amount of charge from one position to another. Okay? You can also say it is the product of electric force and the displacement. Okay? In the direction of displacement, whatever. But here is one. Since it's only one mark, you can just use whatever you use. Now, define electrostatic potential energy. Electric potential energy is the same as electrostatic potential energy. Okay? It is, what is it? It is the amount, here, this one is the amount of work needed to move charge against the electric field from a finite position or from infinity to R. Okay? So it is the amount of work needed to move. Here, this was the work done on a charged particle, okay? In moving a charged particle from one position to another. From one position to another, this is electrostatic work. Electrostatic potential energy is now the work done, yes, or the work needed to be done, or the work needed to move charge from infinity to a position, but it should be against the electric field. So it's to move charge against the electric field, from infinity, or you can say from a finite position, or in brackets you can say infinity, okay, infinity to R. From a finite position or from infinity to R, this would be the electrostatic potential energy. It's the work done when you move a charge against the field. Remember to say against the field. From infinity to R, you are done. That is the electrostatic potential energy. Okay, that is going to be the electrostatic potential energy. Now, what about here? Define electrostatic potential. So this is now potential only. For potential, it is V. Potential energy, electrostatic potential energy is U, right? And when we talk about it as delta U, the change in it. So this is, what is it? It is the amount of work done, or the amount of work needed to move a charged particle against the electric field from infinity to R. That's enough. You can say that. Here it is the work done. Okay, it is the amount of work that is done in moving a charge from one position to another. Okay, work done. Here it is the work done. Here it is the work needed to be done. Okay, or the work needed to move something. So now what about electrostatic potential now? Only the potential. Okay, so here this one is no longer just in moving. If you see here, it is the work to move charge. They didn't give us anything. It is the amount of work needed to move charge against from infinity to R, right? But electrostatic potential now, not potential energy, but electrostatic potential is the same thing, but it is the work required to move a unit charge. Unit means one. So when we say unit charge, we mean 1 coulomb of charge from infinity to R. Okay? From infinity to a position. R just means a position in the field. Okay? So I'm actually just going to copy this one. I know you won't forget it. I'm just going to actually copy this definition, put it here, and just change one thing. So I'm going to put it here, make it a little bit smaller, of course, so that it can fit. Reduce the size of my text. All right. Now when it's like this, so it is the amount of work needed to move unit charge. Okay? Unit charge, which means 1 coulomb of charge, right? Against the electric field from infinity, you can say from infinity to a given position in an electric field. Okay? So you can even say here from a finite position or infinity to here R, we said it's a given position to a given position in an electric field. Okay, same. So work done. It's so simple. Work done to move charge. work needed to be done. Sorry. So it's work needed to move charge from against the electric field, of course, from infinity to a position. Here it is work done to move unit charge from infinity to a position in an electric field. Done. Okay. Now here, of course, after that, then you can see this other definition, which is saying define capacitance. Okay. Define capacitance. So what is capacitance? It is just Q divided by delta V. So when we define it, is the ratio means division, right? The ratio of charge on one of the plates to the delta V, which is the potential difference between the plates. Okay? Because we know C is equal to Q over delta V. Okay? I'm going to do it in the next video maybe. Goodbye for now.